Hello everyone. Today we will be talking about circular dichroism. Okay, so circular dichroism is basically a technique which is used by using the various polarization of the light, and how we are going to achieve, what is the basic principle, what is the application areas, we are going to explain in today's lecture. Okay, so to start with, first, this is a electromagnetic spectrum. So electromagnetic spectrum is basically, you can see it is distributed over some numbers here, which is the frequency representation, and based on the groups of frequencies, they can see they are also classified into the types of waves which you are able to see here. So as the wavelength increases, okay, so from this side you see the gamma rays, then the x-rays, the ultraviolet rays, infrared, microwaves, and followed by the radio waves. So the radio waves, you have the wavelength which is the longest, and the gamma rays, which is the wavelength which is the shortest here. Okay, now we all know the importance, or the usage of different types of these waves in our daily to day life. For example, we go to a hospital to get an x-ray done. So x-ray is basically when you have some fractures in the bone, when you have some problems in bones or hard tissues, then x-ray is a very useful technique, and from there we find out whether there is a crack or there is an internal injury, without even doing a surgery, without even making it invasive in nature, right? So x-ray beams or x-ray rays goes through the hand or the part where it has been damaged or injured, and then we get the x-ray image. For example, you see this is a hand and we are getting the bone images of the x-ray. Rather, on the other side, if you also see, there are other applications, like you go to the airports, you go to the railway stations where you have scanners. So the scanners, whatever luggage you are carrying it, we want to get it scanned through it, and it is also done through different types of rays you can see here. Then comes, I have highlighted here, you see, from 400 nanometer to 700 nanometer, a very special, or you can say the bandwidth 400 to 700 is called as the visible spectrum. Now the visible to whom? Visible to human eye. Okay, so this is the visible to human eye spectrum from 400 to 700 nanometers, and this is distributed in the form of a Vibgyor. Okay, so from ultraviolet to the red and the far red, you can see here, and then for eventually going to the near to IR, and then finally to the IR. Okay, so that is the entire distribution in the increasing wavelength order. Now there are also applications, like you have mobile towers, you have like FM radios where radio waves are used. So this different types of waves, they are based on their property, they have been capitalized, they have been used to, for different communication devices or security devices or treatment devices, diagnostic devices. So they have been capitalized, right? And apart, or in comprising the entire spectrum, if you see, to human eye the only visible range is 400 to 700 nanometer. So this is the bandwidth which is important, and that too, if you start from ultraviolet to blue, then to green to red and far red, so that would be the distribution with increasing order of the wavelength. Okay, now if we simply represent a sine curve of electromagnetic spectrum, then what we see here is, you can see here, so this is basically, a pattern of the wave, and in this, if we want to understand what is basically one wavelength, then what we do is, you take the same starting phase, or you take the same two phases, and then you calculate the distance between them. Okay, now to make these things a little bit simple, so you see here, this is a starting phase which is in the up direction. Gradually there is an increase and then coming back, and the same phase you can find it again at this point. So this from here to here, this is actually a lambda, or the wavelength, one wavelength. So what do you mean by a long lambda or a shorter lambda is, if a wave has a longer wavelength, then this distance will be more. Okay, and if we mean to say a short wavelength, then this distance will be comparatively less. And based on this lambda, in nanometers usually it is taken. So based on this lambda, we say it is a long wavelength or a short wavelength, and this is a comparative, because if you say 400 nanometer is a short wavelength, but that too comparatively in the visible spectrum, and 700 is the longest comparatively in the visible spectrum again, right? So apart from the wavelength, there is another what you say property, where you see here, this is the amplitude. So amplitude is, it's like a wave. Okay, now if you see here, this wave, this is the maxima here, and then it goes from the positive, comes to the base, and then again goes to the negative side. Okay, so this is basically the amplitude. So the amplitude is basically the intensity, the other term can be, and this intensity you have to calculate from the height of this one amplitude, right? And if you say, and this is over a progression over a time, so at t0, if this wave starts, then it will reach, or it will progress with respect to the time, as t0, t1, t2, t3, t4, and keeps on moving in with respect to the time. And that is why this is the scale with respect to the time, and this is the wave propagation direction. Okay, so if you see the arrow, this is the wave propagation direction, right? Now here we have basically another two terminologies. If you see on the top, this is the high. So when there is a wave, the top of the wave is called the crest, and the bottom of the wave is called the trough. You see here the crest and the trough. So this is when I think all of you have seen sea waves. So in that case also, you have the wave, the height of the wave, maximum height of the wave, that is the crest, and then there is a dip, and this dip is not the baseline, it is less than the baseline. You see here, this is the baseline, but this dip goes beyond the baseline. So practically, if it is a this propagation, what happens is, the height of this crest and the height of the trough should be equal. Okay, and that is where the normal propagation of the waves takes place. But there is another important thing which has to be also mentioned here. There is another thing which needs also to be mentioned here, is basically the electromagnetic spectrum. So the electromagnetic spectrum is basically two components. You have an electric component, you also have a magnetic component onto this electromagnetic spectrum. Okay, now from there the terminology electromagnetic spectrum has come. So if you see in this animation, you have the wave propagating in the x-axis. Okay, so the propagation, or the direction of propagation of the wave, is in the x-axis, and you have YOLO, you can see this blue, sorry, and you have a blue wave, you can see here, and a red wave, right? So if I see the static diagram, I see this is one wave, you can see, as I described in the previous one, in this plane, and there is another at the orthogonal plane, where you see the propagation of this particular wave orthogonally to it. Okay, now when you have a magnetic and a electric component, the direction of propagation is, yes, obviously this one, but the wavelength is, you can see here, so this will be one wavelength and this will be another wavelength, right? But what I mean to say is parallelly or simultaneously two components are always there. You have the electric component, you have the magnetic component, right? And the electric and magnetic component together gives the name as electromagnetic spectrum, right? Now if you see here, what is the electron or the electro component rather is this blue one, where you see it is in E. Now this propagation, you see here, either it goes up, plus up, or minus, plus up or minus down, right? So this is the propagation which you can see. And if you see for the B, which is the magnetic part of it, the magnetic part goes in this side and this. So it is like orthogonally, one perpendicular to each other, and one goes in this plane, another goes in this plane, plus up, minus up, other goes in this plane, plus side or minus side, right? And that is how the entire, the plus Z or the minus Z, that would be a propagation for the B here. That is the magnetic spectrum of it. Okay. So keep this in mind, because this is going to be quite handy when we go ahead and understand how polarization takes place, how different techniques you are using it out of the electromagnetic spectrum. Now, what is polarization of light? Now, what do you understand by polarization? I'm getting it like in terms of terminology. Okay. When you have a light source, so any light source, you have a lot of wavelengths coming out from that light source. They're all random. Their directions, their phase, everything will be random. So we need to have a light source which is polarized onto a particular plane. Okay, so I'll elaborate it in a little expanded manner with some examples. If you see here, in unpolarized light is basically direction of oscillations are random. I know that changes in a same plane with time. Okay, so same plane, but with time the direction of oscillations, either it is up or it is this way, it keeps on changing. It is very dynamic, and that is why it is an unpolarized light. In a plane polarized, suppose this is a plane or this is a plane, in a plane polarized light, the magnetic and the electric field components oscillate in a definite plane being perpendicular to with each other. So any propagation, the direction of propagation will be fixed, but at a given time the propagation of the magnetic and the electric field will be always perpendicular to each other, right? And then comes, so when it is in case of a plane polarized, it is a single plane I'm talking of, right? But when I'm talking of a circularly polarized, so here comes the spherical part, the circular part. So circularly polarized light, the magnetic field remains oscillating, but the electric field vector changes direction in a rotary motion. This is something interesting. Now see, in case of a plane polarized light, the direction of propagation is in this plane, and in this plane the wave is moving, and you have the oscillating electric component as well as the magnetic component perpendicular to each other and moving in the same plane. But when I'm talking of a circularly polarized, what is happening? The magnetic fields remain oscillating in the same plane. The magnetic field will be in the same plane, the B I'm talking of, but the E oscillation will not be on the same, again on the perpendicular to the magnetic field, but it will be rather a circular motion. So, or it will be in a rotary motion. Okay, so how we are going to do this? Now for example, you see this is a beam of light, it's mixture of all the wavelengths, right? And it is an unpolarized light. Now when you put a polarizer, is basically this polarizer will allow a one plane polarized light to pass through it, and this is one plane polarized light which is being allowed to move ahead, and rest of the non-polarized light is screened out or stopped at this point. Now if you see, so this is basically a mixture of all the things, and because of this linear polarized light with one plane of oscillations, you are getting this particular movement. And why it is happening? Because you have a polarization filter with vertical passage. So this is the straight vertical passage I'm giving, so that one particular plane of oscillation is allowed to move ahead, and I get a polarized light. So this is a plane polarized light. Okay, and also not to forget, this is just one propagation of the light, but it is always having the two components, the electric as well as the magnetic component, right? So that is always there inherently, but this is overall the plane propagation of oscillation of this particular wave which I am trying to show here. Now When I'm saying a plane polarized light, so a plane polarized light with a linear polarization, you see this is the X and the Y. And you see this is basically the diagonal between the xy, and in this direction the polarization is being taken place. So this is the z axis, and you see either it goes to the x or it goes to the y side, or basically it goes to the diagonally of it, and the propagation is in this motion. So it is in this straight plane, and it is a linear polarized light, as I have been telling in the previous one also. But if we have a circularly polarized light, so what will happen is, in circularly, so xy, same xy plane. Now you see here the plane polarization is circular, because you see this is basically in this direction. So the movement of propagation of the polarized light is not linear like this, but it is circular. You see this blue arrow, it is circular in propagation, although the direction of propagation is same. You see here the direction of propagation is z here, the direction of propagation is z here, again same. Okay, so the direction of propagation is same for linear, direction of propagation is same here. Now there is another form, is elliptical. You see here this is not a circle, but it is little bit more skewed or more elliptical in form, and that is what it is called elliptical polarization, right? Now another thing is, you see this is basically taking place in the clockwise direction, right? So in clockwise direction you have it towards the direction of the clockwise, but this can be also in the other side. So you can also have a circularly polarized light which is anti-clockwise. That is possible. So based on that, what will happen, instead of having going this side, it will try to go in the other side, which is the anti-clockwise direction, right? Okay, so in the circular, so this is, you see the plane of propagation is the z, the direction of propagation being the same, but the only difference is, you see now the propagation is in a circular format, and it is having a rotating electric field rather than a linear electric field moving ahead, but a rotating electric field, and the oscillating magnetic field will also be moving along with it. So the direction of propagation keeps same, the magnetic field propagation will also keep same. Only thing is the electric field, which was always going in one plane, instead of that it goes in a circular fashion and then moves ahead. Either it goes in the rotatory, in the anti-clockwise movement, or it goes in the clockwise movement. So based on that, we always say a right hand rotation or a left hand rotation. That depends on the direction of the rotation of the circularly polarized light. Now again, if you see here, so in circularly polarized light, this is what happens is, and the direction of propagation, but it is in a circular pattern. Okay, so again coming back to a polarized electromagnetic radiation, what will happen, you can have grossly two differentiation, a circularly polarized light, or you can have a linearly polarized light. If you are having a linearly polarized light, then it is in one plane, there is no doubt about it, and there are no problems or if and but about it, right? But if you have a circularly polarized light, then there are two options again, either it can be right-handed or it can be left-handed, or rather it can be right-handed or clockwise, it can be left-handed or anti-clockwise. That can be the two directions, because these directions are also important depending on what information you want to take it, because when we see in stereochemistry that this two directional circularly polarized light gives two different informations out of your structural patterns and stereochemistry. That is why the left and the right handed are important. Now see here, this is basically what I was trying to say. If the direction of propagation is the same, it is the same, but this circulation of the electromagnetic or the electro part of the wave, what happens is, if this is in this opposite to the clock, then it becomes an anti-clockwise, and if it is towards the clock, then it becomes a clockwise, and that is the only difference here. Now source of circularly polarized light, it has to be first what do you say, unpolarized light, and then from the unpolarized light you get a plane or a linearly polarized light, and from the linearly polarized light you get a circularly polarized light. And that is why you can see here, from this is the direction of propagation, this is unpolarized and then becoming a linearly polarized, and finally you are getting a left-handed circularly polarized light. Now there's a small interesting fact here. In nature, there are animals which can produce, this circularly polarized light. So for example, golden scrap beetle like Chrysina gloriosa. Okay, so this is an animal, and there are a few other mantis shrimps have been found which are capable of generating a circularly polarized light. This is something interesting, and in nature they are capable of doing it. So this is the the beetle here, which you can see they produces this one. Now coming to the circular dichroism spectroscopy. Okay, so now we have understood how circular, you say, propagation of, or a circularly polarized light propagation is being done. Now how we are going to use this to get a information. Now circular dichroism spectroscopy is a form of light absorption spectroscopy which is used in determining molecular behavior in a broad spectrum of perturbation by measuring the difference in absorbance of right circularly polarized and left circularly polarized light. Right, so now what happens is the same sample, you once give a right circularly polarized and then you give a left circularly polarized light passing through it, and then you get an absorbance, and based on the difference in absorbance you get informations. Okay, now what is the mechanism here? Now electric field of a light beam causes a linear displacement of charge which it interacts with the molecule. Correct. So when electric field of light beam causes a linear displacement of charge when it interacts with a, basically when it passes through a molecule. The magnetic field of light beam causes circulation of charge, right? So the magnetic field will cause the circulation of the charge, and these two motions combine to result an excitation of electrons in a helical fashion. Okay, but the radiation used being chiral, it interacts in different fashion with a definite chiral entity. So we have to also understand about the chiral entity of the structure. If it is present, what is the, or optically active, there has to be a chiral carbon, there has to be a chiral molecule, or which is an optically active molecule where it interacts with it. Okay, and after the interaction the electric field vector traces out an elliptical path. So circularly polarized light becomes elliptically polarized light. Okay, after the interaction. Now let's see how this is happening. It's step by step I have told you, but let's see how it is actually happening. Okay, so this is basically a schematic diagram which I've tried to show it to you in a very simple manner so that you get the basic concept behind it. You see a high intensity source of light is there. Okay, and from this light source, what is happening, whatever light is coming, it's entirely unpolarized light. So there are a lot of mixtures, then we need to do a monochromator and a linear polarizer, so to get a linearly polarized light from this. And once it you get a linearly polarized light, okay, what you do is you try to get a either a right-handed circular polarized light or a left-handed circular polarized light. So we just make it short is RCP and LCP. Okay, so RCP and LCP we get it, and this RCP and LCP we pass it through the sample of interest. So it can be any structure, any protein, it can be any, but it has to be optically active. Now optically active comes with the chiral carbon and the stereochemistry. Okay, I'm not talking in details, or I'm not describing in details what a chiral carbon and how optically active is, but as of now just remember it has to be optically active. So what happens when RCP and LCP both are passed alternatively, either of them gets absorbed and there is a detector which detects this difference, right? So which detects this difference, and based on that, so we are getting the information in form of a spectroscopy. Okay, now when passing through an optical medium or an optically active medium, the speed between RCP and LCP light changes along with change in wavelength. So the wavelength, because what changes, the wavelength changes either in the LCP or the RCP, the wavelength changes. You can see the lambda L or lambda R, and with correspondingly their absorbance rather also varies in both. So we can see the difference here. Now the wavelength dependent difference of absorption.
okay, is measured and plotted to get the CD spectra of the sample. So what is happening is you see the absorption difference in both, and difference in absorption is calculated to get the spectra. Okay.
Now coming to the application part. Now why this is very important is, in terms of application part, is to know whether the protein is folded or not. If so, then characterization of its secondary, tertiary, structures and its structural family is also important. We can compare the structure of the protein obtained from different sources. So I have one source, I can know the structure of it and I can compare it with the other one. To study the conformational stability of a protein under the various perturbations. Okay, so may it be different environmental conditions like heat, denaturations, or stabilizers, or change in pH, whatever it is. So we can see the conformational stability of a proton, we can study for that. And also to study the effect of protein-protein or ligand-protein interactions. So how stable they are, what are the types of interactions, we can all study this with the help of a circular dichroism spectroscopy. Okay, so first thing is, yes, we can see the number of structures. So it's a simple protein or a folded protein, is a primary folding, is a secondary folding, tertiary folding, what type of folding it is, we can also study that. We can compare the same foldings with a similar type of protein which have the similar foldings, and we can see these foldings, how rigid, how robust it is, depending on the various perturbations are there externally, like a pH change, like a temperature. Okay, so those things are also seen. And finally, obviously, the protein-protein and the ligand-protein interaction stability. Now if you see, this is basically the for spectroscopy, you have to understand where are the regions and what are the wavelength specifically you are getting it. So this is a spectrum, and in this spectrum, if you start from here, it's also 100 nanometer to 950 nanometer. So again, in the vacuum UV, in the near UV, this is the range 100 to 200 nanometer, near UV 250 to 350. Then you have a far UV where 200 to 250 nanometers. You are going for a UV visible, then it is something around 350 to 750 nanometer, and then you have the near IR, which is 750 to 950. So that is how the distribution is there. So you, when you get a peak to this regions, you can understand what are there. Okay, now classifications. So if I classify based on the wavelength pattern, so what I get is, if you see the far UV CD, so 200 to 250 nanometer, that is the range. 200 to 250 nanometer is used to investigate the secondary structure of protein. So change in protein secondary structure as a function of temperature or concentration can be known, right? And which allows you to understand, or which allows you to explore the enthalpy, which allows you to give or study the Gibbs free energy of process. So these are in the range of 200 to 250 nanometer. Now near UV or CD, we have a 250 to 350 nanometer spectra. So in this region, what information you get is, you get the tertiary structure information, and also the nature of the prosthetic group present in that protein. So what is the nature of the prosthetic group which is present in this particular protein of study, you can also find it out. Coming to UV visible 350 to 750, which is quite a broad range, is the visible region is only found when metal is in chiral environment. So when any metal is there in the chiral environment, you get in this region, and free metal ions in solutions are not detected. So free metal ions are not detected, but it has to be in the bonded, and this can be used to detect protein bound to metals. So if the protein is bound to some metals, we can study here. Then finally the near IR CD 750 to 950, and it is used to investigate the geometric and electronic structure by probing the metal DD transitions. Okay, so this is the final or the furthest one from 750 to 950 nanometer. So if I see a superimposed circular dichroism spectra of native as well as a mutant S collicolor, so this is basically the two comparison. Okay, and you can see here the far UV and the near UV, and here what you are seeing is, you see the differences. So when you have, as I said, you can compare, so you can compare the mutant as well as with the native, correct? So you can compare the mutant with the native and find out what are the differences are actually taking place, and then you can see in the far UV and the near UV region. Okay, similarly I'll give you a spectra. This is a represented spectra. Here what you have is basically you can see the blue, red and the green, and it will tell you about the folding. So you see the blue one is basically the alpha helix representation, the red is the beta sheet, and then the random coil in the form of a green spectra. You can see here. So this is the CD and this is the wavelength with respect to the x-axis, and this is the pattern of distribution. It's an example, or you can say a very as an initial representation of how the CD spectra would look like, and this is how it is. So this is another one where we are seeing it in the form of a oligomer or a monomer, and you can see the distribution here in the red and the blue one and the pattern. So oligomer and monomer, if it is a single, then if you have a multiple, then what are the changes in the degree, so you can find out with respect to that. And finally, yes, ligand DNA, as I said, protein ligand interaction, DNA ligand interaction, so all these are also possible. Here you see here ligand interaction, you have the free base, you have the cobalt porphyrins, the copper porphyrins, the zinc porphyrins, so all these things are there, and you can also see the different sequences. So in case of a DNA sequences, in DNA sequences, what are the A, T, pattern, and based on that, these patterns can also be matched. The sequences can be matched. So DNA ligand interactions, protein ligand interactions can also be studied here. And obviously drug protein interaction, yes, so these are two different drugs. You can see here ibuprofen and diazepam.
This too, you see here how it is, interacting with the protein. What is the pattern? In this case, it is interacting, so it's going hand in hand, but here you see the differences in the spectra,
and then you study how they are different. Okay, so lastly, the advantages: minimum quantity of sample you are using, it you are not using much, does not require extensive data processing, and can be effectively used in presence of multiple cofactors. So when you have a multiple cofactors, it can also be used effectively. There are no limitations onto that. So here you do not require much sample. Your minimum sample is good enough, and do not require extensive data processing. Whatever you get it, but there is also complications and disadvantages to it. You have like carbohydrates cannot be easily detected. So carbohydrates, you have a lot of chains, and you have a DNA L rotations are also there. At times, it is difficult to study with CD. Aqueous buffer system used in CD often absorb in the range where structural features exist. So if you have an aqueous buffer system, it overlaps with the region where structural functions are there, and it is very difficult to separate these two informations. System should be completely devoid of oxygen to perform the experiment below 200 nanometers. So if you're going below 200 nanometer, there should not be any oxygen there. Then selection of the buffer, there are selective buffers are there, like phosphate, sulfate, carbonate, acetate buffer cannot be used until they are prepared in the range of 10 to 40 millimolar concentration. You have also solvent selectivity. Large organic solvents, CHCl3, CH2, CH2Cl2, etc., they cannot be used in this case. And finally, the lamp which you are using for the light source, there has to be, instead of like a xenon arc lamps used for high pressure short arc, xenon lamps are essential for doing the UV CD spectroscopy. So you need to have a high pressure short arc xenon lamp instead of an ordinary xenon arc lamp. Okay, so these are some of the references. You can refer to these references, and you can have much in-depth information about the CD spectroscopy and how best you can use it for your work. Thank you.